Hello, and welcome to my next webinar on C++ STL by example. Today, what we're going to do is continue our discussion about STL sequential containers. Yesterday, we talked about STL vectors, which is one of the most common STL sequential containers. And today, we're going to expand our discussion to cover deques and lists, as well as several other classes such as strings, bitsets, and valarays, that while not strictly part of the STL, have certain interesting characteristics that are in common with STL. So without further ado, let's go ahead and get started. I will start by sharing my screen, and let's see, share the screen. And you can see here that the code we're going to be looking at is available at this link, which is the C++ STL S-03 folder. And today we're going to start with the 3.4 folder, and then we'll go on from there. All right, so let's go ahead and share my IDE. And I've got the first piece of code available, ready to go. This code will describe how a deque works. First, what's a deque? A deque is a double-ended queue. And a double-ended queue is a more sophisticated data structure than a vector, which only really supports efficient adding at the end and removing at the end. Unlike the vector, the deque supports adding at the end and removing from the end, as well as adding at the beginning and removing from the beginning. As with vector, you can also add and remove from the middle, but that's not efficient. But what it works under the hood is it's basically a double-ended queue, and so it's arranged to be a more sophisticated data structure that can grow and shrink efficiently in either direction. There's certain characteristics that deques and vectors have in common. In particular, the individual elements can be accessed by their position index, and you can also iterate over the elements in any order, backwards and forwards and so on. So the main difference between them is you can put things at the beginning and remove things from the beginning efficiently. Internally, deques and vectors work quite differently, though. A vector is just a contiguous chunk of memory, so accessing its elements using, say, the subscript operator is very efficient. In contrast, deques are not as efficient. And so as a result, they have extra overhead, not wildly amounts of extra overhead, and there's still constant time operations to insert and remove items at the beginning or the end. However, they're not as efficient as vectors. So you have to be aware of that. And they're also not allocating all their memory internally in a contiguous way, which is also important. So what we're going to do now is take a quick overview of what actually constitutes the interface for a deque. You can see here that a deque is templated. So it has a type name T template, and it also has an allocator. So these parameters are identical to what you would find with a vector. The T is obviously the data type that you're using to instantiate the deque template with, like int or double or employee record or whatnot. And the allocator is something that's used to allocate the memory. By default, it uses the operator new and delete that comes with C++ and uses the C++ global free store out of the box. Most of the methods between vector and deque are the same. There's a few differences. You can't reserve space in a deque the way you can do in a vector, and you can't check the capacity for a deque the way you can in a vector. And in addition, there's a couple of new functions as well. There's a push front and a pop front pair of member functions. And those, of course, are the ones that correspond to the ability to efficiently add and remove elements here. So let's go ahead and take a look at an example. This is a very, very simple example. We go ahead and make a deque that's initially empty, and let's make it a deque of floats. And then we're going to demonstrate how you can iterate through the range 0 to 6, or 0 to 7, but 7's not included. And we're going to go ahead and push something at the front and push something at the back. So these are basically going to be kind of a palindrome set of values, if you will. It basically will be the kind of a mirror image of the values. And then we go ahead and use the range-based for loop here to print all the elements of the deque out. Of course, I could use iterators or other things, but I'm going to use the range-based for loop. And of course, I could also say auto here. As we've talked about previously, this goes ahead and tells the compiler to auto-deduce the type. So let's run that particular piece of code. And you can see here that we end up with the following output, which is what we want. It's kind of a mirror image or a palindrome of sorts, where it's got 6.6 at the beginning and end, and then 5.5 at the next slot, and 4.4 and 3.3 and 2.1, or 2.2 and 1.1 and then 0, 0. So this is just illustrating how you can use a deque to add elements at the beginning or the end. And to do it efficiently, of course, which is kind of the goal of all this. So that's basically the simple example of deque. Let's go ahead and take a look at some other examples that are perhaps a bit more interesting, and they will demonstrate some other features of deque. So this is another example. When you think about deque and you compare and contrast it with vector, why would you pick one versus the other? So as a general rule of thumb, I think, as I mentioned before, if you just need to be able to do random access and you're just adding things at the end, I recommend using vector because it's more efficient, more space conserving, and so on. Also, if you want to reserve a large chunk of data because you know how big the vector will be in the first place, you can use reserve on it. Also, keep in mind that when you create a lot of elements with deque, then when the deque is destroyed, it's going to take longer to reclaim the memory than it will for vector. And the reason for that is that vector always has a pointer to one contiguous chunk of memory. So when its destructor runs, it just has to delete that particular item. So that's really fast. It gives the whole kit and caboodle back to the free store in one fell swoop. Conversely, deques allocate chunks of data. And so when deletions occur, it has to delete all the chunks. Not the end of the world, but it's something to keep in mind. Another couple things to keep in mind is if you're using data structures or using algorithms that require access to the front of the data structure to insert or remove, a deque is going to be a lot more efficient than using a vector because it's built to work that way. And then also keep in mind that the vector operations to get particular elements like subscript operator or the operator, at member function, those will be a little faster because it's really a very fast, constant lookup with very little overhead in order to be able to get elements of a vector like vector v sub I, where I is in the range. Whereas with the deque, it's still constant time, but it's not quite as fast because there's a few indirections that take place. Deques are often implemented with something called a cactus stack, and that allows them to grow efficiently at both ends. So here's another example. This example is going to start with an empty deque, and we're going to go ahead and push a bunch of characters in there. Basically, we're going to push A, B, C, D, I believe, and then we're going to go ahead and print those out. And again, today's C++ programmer would probably use the auto keyword here, so we'll do the same thing. And probably should call this something other than I, but we'll leave it as it is. And now let's go ahead and do some interesting operations with iterators to our deque. And you're going to see how deques support so-called random access iterators. And this is very cool because it lets us be able to kind of move around in the deque and access different elements. So what we're going to do here is we're going to say a deque begin, which is going to get us an iterator to the beginning of the deque. And then we're going to add 2 to it. And this demonstrates what's known as random access iterators. Deques and vectors both have random access iterators. Most of the other STL containers have bidirectional iterators or some other form of lesser iterator. Random access iterators are the zenith of iterators in STL because they can be used, in essence, the same way you can use pointer arithmetic on pointers to arrays. You can plus them, you can plus equal them, you can add to them, subtract them, you can do all kinds of cool things. This is illustrating also 2 different ways to use the iterator. The first way we're going to do it for the IT1 is to use the iterator trait. So you can see here we have deque, char, iterator. That's an iterator trait. And then we can also see how we can use the auto keyword. Old school STL programmers probably are more familiar with using traits. We'll talk more about traits when we talk about iterators. Basically, think of traits as a name or a type def that's associated with a container that then defines something about its metadata, in this case, the type of iterator that it uses. So kind of old school developers probably would gravitate towards using explicit iterators, as I show here for IT1. But the more modern way of doing things in C++ and STL is to use auto. And as you can see here, it's less typing. And you can also switch back and forth. If you take a look here, you can go between auto and the full Monty, if you will, for the iterator traits. This one we're going to start at the beginning, and we're going to skip over 3 elements. And then we're going to go ahead and print the contents of the elements at those locations pointed to by the iterator. So you can think of iterators as basically kind of, smart pointers. That's one way to think about them. Not the only way, but one way to think about them. So in this case, we can dereference the iterator, smart pointer, and we'll print its values. So far, so good. Now we're going to do something else. We're going to go ahead and insert an element after IT1. So wherever IT1 points to in our deque, we're going to insert a new letter, in this case, a capital X, at that location. And then we're going to go ahead and print the contents after that. So we printed the first contents earlier. Now we're going to print the second contents after we've added an element. And then the very last thing we're going to do is we're going to print out IT1 and IT0. We're going to dereference both of those iterators. And this is interesting. Some implementations of STL will actually crash at this point. And that's because out of the box, STL does not support so-called robust iterators for data structures like deques and vectors that could resize themselves. And so that's where you have to be careful. So normally we wouldn't want to write this code. I think this particular implementation runs correctly or runs without crashing and gives the right results. But be aware that you have to be very careful for deques and vectors. If you've modified the deque or vector, that may invalidate iterators that are pointing into the locations. And this will become a little bit more clear when we talk about iterators later. So let's take a look at what the results are after we ran the program. So you can see the original sequence was A, B, C, D, E, and that's because we went from 0 to less than 5, so that's 5 locations. We added the value of capital A to each one of those numbers, so we got letters in response. Then we went ahead and printed out the iterators that we got, and you can see that we skipped over the first 2, so we got C for IT1, and we've skipped over the first 3, so we got D for IT2. And then we went ahead and inserted X, and we inserted X, basically, I guess actually it puts it before IT1, not after. So you can see there's IT1, which pointed to C. So now X has been inserted there. Now keep in mind that this insertion is not that efficient if you do it in the middle of the deque, because the deque has to kind of move things apart to open up some space for the new value that we're adding here. And then when we print out the results at the end, you'll see we get IT1 is X and IT2 equals C. And as I mentioned before, you're not guaranteed that this code is going to work, but it looks like the implementation that comes with the G++ compiler that I've got here works correctly for that. But be careful because it's not really defined to work that way, I believe. Okay, so that's another set of examples of deques. You can see that they have some interesting properties. Let's go ahead and take a look at yet another deque example. And this particular one is going to show some interesting characteristics using traits. And here's the code. The code is actually pretty simple. We make an empty deque. We add 3 to the end, and we put 1 at the front. So now it's got 1, 3. And then we go ahead and we insert at the position that is going to be between 1 and 3. So we put a 2 in there. And now we go ahead and put a 0 in the third location. So let's go ahead and run that, just see what the results are. And you can see that the results, remember we had 1 and 3 in the beginning, then we stuck a 2 between those two things, and then we said deque sub 2, which is the last element in this current deque, because everything in C and C++ and Java, for that matter, has to start with 0. And so we end up with the values 1 to 0. And then when we go ahead and we call this method print, and we're going to print the deque. And let me show you how we do print, and this is kind of interesting. Notice what we're doing here is we're passing in a const ref to the parameter D. So we're passing in a const ref parameter. And what that means under the hood is that instead of making a copy of a deque, what happens is that calling by reference or const reference is going to take the address of a deque, and it's going to pass it in such a way that it's treated as a const ref. And that means that its value can't be changed in the method that's being called. So this is a time-honored way in C++ of being able to optimize passing objects by not actually having to make a copy of them. The data lives at the caller location, and then it gets passed in. So down here, what we're going to do is we're going to print out the number of items in the queue, which is d.size, and that works fine. And that's because size is a const member function. If you take a look, this is the implementation of size inside of the deque implementation, and you can see that size is a const t. All that, I'm sorry, it's a const. What const means is that it won't make any changes. That method call won't make any changes to the state of the object for which it's invoked, and therefore it can be called on a const ref. Then what we're going to do is we want to iterate through every element in the deque and print the elements out. And just for kicks to get started with, we're going to go ahead and do this with an iterator, just so you can see what it looks like. So in this case, we say d.begin, and notice that d is a deque, that's a const ref, and therefore d.begin is going to have to return a const iterator. And that's because if it was returning an iterator, which it can't do because that's illegal because it's a const ref, then you'd be able to update the value through the iterator, and that would be a big problem because you'd be changing its state when it was passed as a const ref. So instead of having iterator, we use a different trait. Remember, traits are just these little metadata names that are associated typically through type defs in containers. We're going to say use the const version of this. And the const version of an iterator for a deque does not have a dereference operation that can be used on the left-hand side. You can only use it on the right-hand side of an assignment statement. So it only has R value references, dereferences, as opposed to L value dereferences. That's the primary difference between const and non-const iterators. So then what we're going to do is we're going to go ahead and iterate from beginning to end and print each value out. Now, there's nothing that forces us to have to use this const iterator at all. In fact, probably a newer practice would just have us use auto, and we just let auto figure out the right type. It deduces it for us. And that's probably how I would write this code in production code. But I wanted you to get the sense of what a const iterator is. And of course, auto is using a const iterator. See if I can make it redo. So auto is using a const iterator, but you don't see that as graphically or as vividly as if we're going to have to put the const in there. And by the way, type name when used in this context simply says that this is a type name, and therefore you can use a trait operation on it. I think if we try to do it like this, it complains and says, let's see, what does it say? It says insert type name. So that's what it tells us to do. And that's kind of some syntactic weirdness of C++. Okay, that's another example. And now I think we have one more example to look at here for iterator, if I'm not mistaken. Let's go with, or sorry, with deque, if I'm not mistaken. Let's go ahead and pull that up. So this particular example is actually a very simple example, but it's going to show some other features that are good to know about. And we're going to talk about them quite a bit more when we start talking about exception handling and exception safety in STL and C++ a little later. So this particular example is going to have two deques of character. You can have my first deque and my next deque. And what it's going to do is it's going to push a bunch of letters to the first deque, and it's going to push a bunch of numbers, digits, not numbers, but digits, the digit version of numbers to the second deque. And then we're going to go ahead and print out the size, and then we're going to print out the contents. And again, probably should use auto here because that's the newfangled way of doing things. And so we're going to print out both the first deque and the next deque. And then what we're going to do is we're going to do a swap. And a swap is a very interesting method. All that swap does is it goes ahead and it swaps the data. And let's see if we can make the IntelliJ, the C-line stuff do swap. It's got confused at this point, so we can't really follow that any further. But basically what it's doing is it's swapping the references in here. And so what it's doing is it's taking the state of the deque, which would include things like its size and its whatever its internal representation is, which is probably a data structure like a cactus stack or whatnot, and it's going to swap the references to those things. So it doesn't actually make a deep copy, it just swaps the data that corresponds to how the implementation is laid out in memory. And once we've done that, and when we run this code, you can see that my first deque now has the contents of my second deque, and my second deque now has the contents of my first deque. So you can see here we start out with 26 and 10. We have 26 letters, uppercase letters, 26 or 10 digits. And then we swap them, and then they've been reversed. Now, it may not be apparently obvious with this simple example what the heck swap is doing for you. But what it's doing for you is it's setting it up to be able to do very efficient and transparent or easy to program exception safety. And we're going to talk more about exception safety in C++ later. And what's good about the swap operations, and let's see if we can at least get this from here. You can see that it uses this no except mechanism. Let's see if we can find that. There you go. So no except. So you can mark methods in C++ as being no except. And what that basically means is they guarantee not to throw exceptions. So swapping won't throw exceptions. And that turns out to be very important when we start dealing with exception safety, as you might imagine. Okay, so that's the end of the discussion about the deque. Let me see if there's any questions at this point. It doesn't look like there's any questions yet. As always, if you have any questions whatsoever, please don't be shy and jump in and you can ask them. Okay, what we're going to do now is we're going to shift gears and we're going to talk about lists. So let's go ahead and look at some list examples. There's just a couple of list examples here. A list is yet another sequential data structure. Like vector, like deque, you can have a list, and it's implemented under the hood as a doubly linked list. Hopefully everybody remembers doubly linked lists from data structure courses you've taken. And that allows us to be able to traverse the list from beginning to end or end to beginning with equal ease and equal efficiency. We'll see that there's also another kind of list called a forward list, which only has a single pointer, and therefore you can only traverse it from beginning to end. You can't traverse it from end to beginning, at least not efficiently. And so, but a list out of the box is a doubly linked list. What doubly linked lists buy you, kind of two things it buys you. One thing it buys you is it buys you the ability to add and remove elements anywhere in the list efficiently once you've found the location you want to put the item in. So unlike deques and unlike vectors where they have to move data around in a linked list, you just have to rearrange some pointers. So that's one benefit. Another benefit is that unlike vectors in particular, lists will only really allocate as much memory as actually is in use, whereas vectors will often allocate more memory on the offhand chance you're going to grow them at the end. So maybe lists are more space conserving, although you also then have to pay the price of keeping these pointers in them. So you have a prev pointer and a next pointer in every node in a list. So that could actually end up taking more space, depending on various factors. The other things you can do is you can iterate in either direction with a list, not a forward list, but with a list. So as a general rule of thumb, use lists if you're going to be doing a lot of arbitrary insertions in the middle somewhere, or other places besides the beginning and the end. But other than that, you can't do random access operations on a list, and that's because the type of iterator it supports is known as a bidirectional iterator. And so you can only do things that advance efficiently by one. You can go either forward or backwards, forward from the beginning, backwards from the end, one element at a time. And we'll see some examples of that here. Okay, here's what the actual data type looks like. It's not too dissimilar to deque and vector. We basically have class list, which is templatized by type name T, and it's also templatized by the allocator. Nothing has really changed at all. And in fact, that's a virtue of STL. It's often the so-called principle of least surprise, where you have common APIs and you can plug and play. And this really starts to show up when we talk more about iterators and we start talking about algorithms. This allows us to be able to use or reuse common algorithms with lots of different types of containers. So here's the example that uses a C++ STL list. As you can see, what it does is it starts out and it makes an empty list of characters, and then it's going to go ahead and push a bunch of characters into the list, basically A, B, C, D, etc., up to the first 10 characters. And then it prints out the size of the list. As you can see, all the different containers have this size method that they share. And then we do the fun part. What we're going to do is we're going to print the contents of the list out, but we're going to do it in a somewhat non-conventional way. While the list is not empty, we're going to go ahead and get an iterator to the beginning of the list, which we use as auto. We then go ahead and print the dereferenced value pointed to by the iterator using our iterator smart pointer star operation. And then we go ahead and we pop the front item off the list. So this is basically going to print the list out in order, and it also has the side effect of emptying the list. And that's important here because the way that this loop works is we're going to keep doing this while the list is not empty. So let's go ahead and run the code. And you can see that here's what we got. We got A through J printed one character at a time, the first 10 letters that are uppercased in the alphabet. So that's kind of demonstrating how this particular example works. And this doesn't really show you anything particularly profound about lists being used to allocate and put memory into the middle. So let's go ahead and see if we can find an example that shows that. Let's go down here and let's open up this guy. And hopefully, yes, this has the right code. So here's some things to think about when you start using a list. First of all, they have most of the member functions that deques and vectors have, except it doesn't have capacity, reserve, and it also doesn't have the random access methods, the operator subscript and the at method. And that's because it's not intended to be used in a random access way. Of course, you can randomly access the elements in a list, but you have to write the code that moves yourself through the list with an iterator one at a time. So it's just not meant to be efficient. It does, however, even though it doesn't support random access, it does support bidirectional iterators. So you can start at the beginning and go to the end. You can start at the end, go to the beginning, and given a point in the middle of the list, you can move it forwards and backwards efficiently. Another nice thing about a list as opposed to a deque and a vector is if you remove items, it doesn't invalidate existing iterators unless you happen to remove an item that's got an iterator pointing to it, in which case that would be invalidated. So let's take a look at an example to illustrate how the list works. And this will also illustrate how you can add things at arbitrary positions without a lot of overhead. So we're going to make ourselves a list. We're going to put a 0 at the end and a 0 at the front. So it's a list of ints. And then we're going to go ahead and get an iterator to the beginning. And then we're going to increment it by 1. And then we're going to put the value 2 after the first element. So then the value of the list would be 0, 2, 0. And then we're going to put some elements at the end, 5 and 6. So I think the result should be 0, 2, 0, 5, 6. So let's go ahead and run this and make sure that my hunch is correct. Sometimes it is, sometimes it isn't. In this case, it was correct. We have 0, 2, 0, 5, 6. And what that's basically saying here is that we were able to insert this element at some point besides the beginning and end. And if you were to look at how it worked under the hood, you'd see it was done very efficiently because it just has to rearrange the pointers in the doubly linked list representation. And then the last thing we do is we just print the contents out of the list. So that's pretty straightforward. Okay, so those are the examples I wanted to look at for list. I would say as a general rule of thumb, vector is by far the most common sequential STL data structure. And then list is probably number 2. Deque, not that widely used unless you really have to grow and shrink your elements at the beginning and the end, and you're not so much concerned with the middle. Okay, what I'd like to do now is talk about a couple of other data structures that come along for the ride. So let's go ahead and take a look at these guys. These are not strictly STL data structures. They are data structures that are part of the standard library and have some characteristics in common with STL. And the first one we're going to look at is very popular, and it's, of course, the string class. So string is actually not part of STL, but it has some characteristics in common. So you can see here that you can assign a string from a character string or a character literal. So we can say string my letters, or just all the letters in the alphabet. And then down here, we can use the range-based for loop to iterate through each element in that list. And I don't think this will let us switch over to using an iterator-like model, but we can easily do an iterator-like model if we wanted to. We can say for auto I equal my letters dot begin, and then we can say I not equal to my letters dot end, and then we can say plus plus I, and then we can say cout star I my letter. Let's call it I guess I said I. End all. I should use something besides I. That's not very intuitive. If I should use C or something like that. Whoops. It would help if I used the right syntax here. This thing. All right. I think that probably does it. Oh, I see what I did. Yeah. Let's try running that. See if we get what we want. Yes. So we are ending up here with the letters printed out. The one thing we lose is we don't have the number, but that's okay. So that was just illustrating how you can use an iterator here as opposed to using the range-based for loop. For my money, in this situation, I would almost certainly go with range-based for loop, but be aware that under the hood, what range-based for loop is actually doing is it's using the iterator mechanisms that are built into C++. It's just wrapping some syntactic sugar around those mechanisms so that they look a little bit more concise and a little bit more clean. And in fact, that's a great example of a common theme throughout programming, whereby programming constructs that were once patterns, like the iterator pattern, get baked into the next generation of language features supported by compilers. So it's basically about automating patterns. Not every pattern can be automated, but this is a good example of one that is. Okay, so that's one example of using a string. Very, very simple example, of course. Let's take a look at a more interesting example. So here we've got a bunch of other features of strings. So you can see that we create a const char pointer with a particular phrase, good night, Gracie. We then go ahead and create a string from that const char star. Then we go ahead and we create another string, passing it in directly as to the constructor. And then you can see we're going to make a copy of string 2 into string 3. So now they're both going to say the same thing. Now we're going to go ahead and create a substring of good night, Gracie, and we're going to snip out the parts from characters 4 to 9. So I think it's going to say good night or something like that. And then we can either do it this way with a constructor, or we can go ahead and use the substir operation and get the same thing. Excuse me. And then we're going to go ahead and look for the string Gracie in our string number 2, and that'll give us back a position. And if the position equals this kind of end position or end pause position, then that's an indication we didn't find it. But if it did find it, it's going to equal something other than end pause. And then we're going to go ahead and do is we're going to erase the elements at this point and then insert this string. So that's going to illustrate a few more things. And then this is going to show how you can append strings by using the plus operator. This is very much like Java, if you're familiar with Java's use of plus for concatenation. And then we can also go ahead and find the first match of a number of characters. So we can say either the capital I or E, find me the first match of these characters in string 2. And it'll tell us if it found a match, where it matched. So let's go ahead and run all that code. This is a bunch of interesting C++ string operations. And you can see what it prints out is good night, Irene. That's what it prints out initially when we do the print. And then we go ahead and say good night, Irene, good night. So we go ahead and print out by putting the stir 4 here. So this is where the first printout gets done. Good night, Irene. We replace Gracie with Irene. Then we go ahead and append string 4, which says good night, which is what we got up here when we did this substring operation in the constructor. And then the last thing we do is we go ahead and look for the character I, and we find the character I at position 15. You can kind of see how this all works. Very cool, lots of good stuff with strings. People tend to use the string class quite a bit if you're doing string processing. So very much like with, say, Java, where string class is very widely used, C++'s string class is also very widely used. The main difference with Java and C++ is that Java's strings are all immutable. So any operation on a string always creates a new string. Whereas, as you can see in C++, you can actually mutate or modify an existing string with operations on it like erase or insert or so on. Okay, we've got one more string example. And let's take a quick look at that. So this is going to show a whole bunch of string functions, and I think I'm just going to go ahead and run the code so you can see what the output is, and then we'll go and look at all the crazy things it's doing. So this particular example is going to make a bunch of strings with just character phrases in it, and we're going to go ahead and do some things to say, is the string empty or full? We're going to print the strings. The string C, which is the one here, that is indeed empty, so that returns a 1 because 1 is true in C++. And then we're going to go ahead and concatenate string A and string B, and then we're going to check a few different fields. We're going to check length versus size versus capacity. And you can see in this particular implementation, length and size are the same, but capacity is larger. And that's because strings under the hood will often allocate more memory than you've requested because they're expecting the string to grow. So they're proactively trying to be efficient about minimizing string reallocations. And now string C, which is what we concatenated this thing into, this is no longer empty, so it's now 0. Then we go ahead and do some other things. We print the first character in string C, which is an A. We go ahead and indicate leading and trailing blanks. So we have a string with leading and trailing blanks, and we can see the length of that. And then we can go ahead and append something, put it at the end. We can put ZZZ at the end of the string, and then the length, of course, goes up, as you can see there. And then we can do some replace operations. What replace does is it goes ahead and will take the contents at a particular location and replace it with other things. So we get some crazy results at that point, where it's replacing the operations at those locations in the ways that we see here. And then the final thing we do is we illustrate some of the find operations. So we're going to go ahead and say, is the substring ABD in this string G? And then we go ahead and print the results of doing that. And we go ahead and look up some other stuff and print results out. And then you can also find various things. Find first not of. So this is saying, find me the first element in this string that doesn't have an A, B, C in it. Or find the first not of, find me the first non character that's empty. Well, you can see that it's the empty string, and so on and so forth. So these are all different ways to manipulate strings. They're very powerful, but somewhat complicated. And people have criticized C++'s string class as being an example of a class that was designed by a committee. And that's probably fair. There's an awful lot of methods in that class. And if you compare and contrast the string class, which was designed by committee, versus a lot of the other classes you find in STL, like vector or deque, which were designed by a much smaller group of people, namely 1 or 2 people, you'll see that the ones that are done by a smaller group typically have more coherent interfaces, coherent APIs, and so on and so forth. Okay, let's see how we're doing on time. We have time for a couple more things. Let's go ahead and take a look at a few more data structures that are not strictly part of STL, but are interesting to know about. So I'm including them in this discussion, even though they don't necessarily belong here in some way. This example we're about to look at is one called a bitset. And as the name suggests, a bitset is a set of bits that's packed and implemented very efficiently to take as little space as possible. And you'll see there's a bunch of operations you can do on bitsets using all kinds of funny operators, all the overloaded operators that you might come to know and love from C and C++. So let me run this code, and then we'll go ahead and take a look at the software that generates this. We make this about roughly the same size so you can see what we got. Okay, So we start out by making a bit set with 16 bits. And you can see if you were to count these, there's 16 outputs in what's shown here. And we're going to give it the initial value of 32, which in this case is going to end up being this binary value. So if you think about what 32 is represented as a binary value, as a bit string or bit set, that's what it's going to be. It's going to have the 1 in that location in the output. And then we go ahead and print out a few bits, and you can see it turns out to be 32 in binary. Then we're going to go ahead and set some of the bits to true and some of the bits to false. And so you see when we take a look at printing this, then we've turned on some bits that weren't set before. Like we turned on bit 0 as true. We took bit 2 and made it false. It was already false. I don't know why we're doing that. Probably would have been more interesting to maybe gotten rid of bit 1, 2, 3, 4, 5, 6, maybe bit 5, because everything starts counting at 0 in C++. So that hopefully did it. There we go. So now we got rid of bit 5. That's been turned off. Then we go ahead and we rotate the bits. So we rotate them so they are rotated by 2. So we're kind of shifting them over. And you can see that what's here was once 1 has now become basically the value of 4. And then you can flip the bits. So all the bits that were 1 become 0, and all the ones that were 0 become 1. We can check to see if there's at least 1 bit set, which there is. We can get a count of the number of bits that are set, and then we can actually index into the bit set and check to see what the values are. So if bit 0 is 1, it means it's on, otherwise it's not on, and we can call test, which is basically the same thing. And you can also actually add bits to integers. So you can basically say, take the value here, which is going to be 1, because we've got a value of 1 in there, and add that to the integer 11, and we get 12. So interesting bit operations. Honestly, however, that's not a lot of uses for this stuff in practice, because the way the bits are actually laid out is not specified. So the ability to use this to actually map onto things like device registers is somewhat implementation dependent. Although I suppose if you played your cards right, you could use this for a higher level way to do bit fiddling that you could then map down to lower level hardware. The last thing we're going to talk about today is valirray. And a valirray is a very interesting data structure, which is kind of like a vector, but you can do operations on it in one fell swoop. So what you can do is you can have a vector, a valirray, and you can say, I want you to add everything in this vector, or I want you to multiply everything in this vector by some value, and so on. So you can kind of think of it like a single instruction, multiple data style processing abstraction. Although, unlike most single instruction, multiple data, or SIMD abstractions, it doesn't actually do all of its work in parallel. Although I suppose you could write a version that did, which would be pretty cool. So let's take a look at some examples. Once again, I'm just going to run this code, and then you can see what the output is. So we're going to go ahead and make a valirray of 10 elements, and we're going to go ahead and assign the numbers 0 through 9 into that valirray. And then we're going to go ahead and print the contents. So the contents show up. There are other ways to do this. We don't have to do this as an array. Well, actually, we have to do it as an array because there's no iterators defined on this, as I believe. I think it says that up here somewhere. It doesn't provide iterators. So you can see why it's not really strictly part of STL. Then what we're going to do is we're going to take the current value array and we're going to shift it by 3. So you can see it shifted everything down and wrapped the contents around. And then we're going to go ahead and take a value array and make a new value array of Booleans, where we're going to make the settings in the new value array correspond to the expression current values in the val array that are less than 5. So we're applying this to every element, and we're going to return a new val array with 0s or 1s set, whether the numbers were less than 5 or not. Then we're also going to go ahead and make a value array, and we're going to go ahead and do some things to it. So we're going to put a bunch of double values in there, and then we're going to go ahead and print the original contents. Then we're going to compute the square root of the values in the val array. You can see what the square roots are for these numbers. And then we're going to go ahead and add the contents of the val array to itself. So we're going to end up with basically squaring the contents. Then we're going to go ahead and subtract 10 elements from that valirray. So every element in the valirray has 10 subtracted from it. Again, interesting abstraction. I'm sure someone had a lot of fun writing the code to do that. I've never really used this in practice, but if you ever find yourself where you need a sequential, single instruction, multiple data class, valirray is the class for you. Okay, so that is where we are going to leave off for today. What we'll do next time, which might be on Monday, depends on how things go at the weekend and the holidays under the COVID protocol brings to bear. But in our next session, what I'm hoping to do is to start talking about iterators. So we've talked about sequential containers. You've seen little snippets of iterators here and there. You've seen things like the concept of an iterator trait. We've seen the concept of a const iterator. You see how you can manipulate iterators much like you would manipulate smart pointers or pointers to built-in arrays and so on. And what we're going to do is really break down what iterators are. And you'll see that there's 5 different categories of iterators. There's input iterators, output iterators, forward iterators, bidirectional iterators, and last but not least, certainly not least, the random access iterators. And we'll talk about how they build on each other. And I'll show you lots of really cool examples using iterators. And there's some really neat stuff there. So the question is, when is the next webinar going to be? It will probably be Monday, I'm guessing. I think we, like most people, are not doing extensive travel for the Memorial Day weekend. So it'll probably be Monday. But please keep an eye out on my website, the STL by example, or STLBE website that I have, and I'll update everything with the dates and the times, and of course also the Zoom link that you can use in order to be able to come and join. Let's see, there might be another question. Let's see, I think that was the question. Okay, well, thank you guys. As always, thanks to everybody for coming. I really appreciate it, and I will look forward to seeing you soon.